Hello, welcome back to Educator.com and welcome back to physical chemistry. So today we're going to talk about the particle in a box. So the particle in a box is a reasonably simple quantum mechanical problem. It is our first dealing with a quantum mechanical system. We're going to solve for the wave equation. We're going to investigate the energy levels and things like that. So it's very, very, very important. What we do here is going to set the pattern for what we continue to do throughout the quantum mechanics. So let's get started. Okay, so let's recall the Schrodinger equation. We had, let me see, that's okay. I'll stick with black. It's not a problem. So we had minus h bar squared over 2m and d squared c dx squared plus this potential energy times the wave function. Actually, I'm not going to put the x on this wave function. I'll leave it like that. Equals the energy times the wave function. So this is the Schrodinger equation. This is the partial differential equation that needs to be, well, in this case, it's an ordinary differential equation because it's just a single variable x. But in general, it's a partial differential equation that needs to be solved for c. So what we're looking for when we solve this equation is this wave function. What is it? And that wave function represents the particle. It is instead of dealing with it as a particle, we're thinking about the particle as a wave, and this wave function, which is a function of x, represents how the particle behaves in any given circumstance. So, now the box in this particle in a box, what we're talking about is the following. Okay, the box. So we're going to be dealing first with the particle in a box of one dimension. So a box is exactly what you think it is. It's just think of a box, and if I drop a particle in there, it's going to be a three-dimensional box. Well, a two-dimensional box is just the plane, and it could be square, rectangular, whatever. A one-dimensional box is just an interval. So the box here in one dimension, so we're going to start with the one-dimensional problem, and then we'll go ahead and extend it to 2 and 3. In one dimension is just an interval. That's it. Is just an interval on the real line. So this line, so let's say from 0 to a, that's our box. So the particle is going to be basically found somewhere in here. That's it. It can only be there. Can't be out here. It can't be out here. That's all this means. Now, we're going to study the free particle constrained to lie between 0 and a. So, the free particle in a box. The free particle in a box. Now, the word free particle here, free particle means it experiences no potential energy. It experiences no potential energy. In other words, V in the Schrodinger equation is going to be 0 in this particular case, so it simplifies our equation a little bit. Experiences no potential energy. That's it. Imagine just taking this particle, dropping it on this interval, and saying, where are you going to be? How fast are you going to be moving? Where is it going? Things like that. What's it going to do? Well, it can only do one of two things. It basically can go this way, or it can go this way. The questions that we pose in quantum mechanics are, well, which direction is it moving? How fast is it moving? And at any given moment, can I tell you where it is? Those are the questions that we want to ask, and these are the questions that the wave function is hopefully going to answer for us. Okay, so free particle means it experiences no potential energy, which means that V of x is equal to 0. So this equation actually ends up becoming the following. It ends up becoming minus h bar squared over 2m, the derivative of this squared, second derivative of that, is equal to e times our wave function c. So I'm going to go ahead and rearrange this and write it in a way that is more convenient for actually solving the differential equation. It's the way that you learn when you actually take a differential equation course, and it'll make sense in just a minute. So I'm going to rearrange this. Basically, we multiply by the 2m, divide by that, bring everything over to one side, and we set everything equal to 0. So it's going to look like this. It's going to be d squared c dx squared plus 2m, 2me over h bar squared times c equals 0. And again, this wave function psi, or psi, sorry, I tend to say psi instead of psi, it's a function of x. It's just a normal function like anything else. Sine x, cosine x, logarithm of x, that's all it is. That's what we're looking for. In algebra, when you have an equation like 2x plus 3 equals 5, you're solving for x, you're trying to find a number. A differential equation is the same thing, except it's kicked up a couple of levels. Now, the variable that you're looking for is not a number, it's an actual function. That's all the differential equation is. It's just a fancy algebraic equation. That's all it is. And in fact, there are techniques that actually reduce these straight, to algebra. So don't get lost in the fancy mathematics here. It's just, we're just solving this. It's a little bit more complicated, but we're just looking for some variable, and our variable happens to be a function. So I'm going to leave off this x just to save some notation. And again, we have to specify x is between a and 0. So that's it. Those are its constraints. It can only be between here and here. We're putting the constraints on it. Okay. So now the question is, how can we interpret this psi? How do we interpret that? Well, we said that, so we said that the wave function, it represents the amplitude of the matter wave. In a previous lesson, we said that it represents the amplitude of a matter wave. Amplitude of the matter wave. Okay, now in classical mechanics, when we square the amplitude of a wave, we get the intensity of that wave. So the square of the amplitude, which this is, represents the intensity of the wave. Represents the intensity of the wave. And I'm going to do it this way. It's going to be psi of x, the complex conjugate, times c. So we're not just going to do psi x times psi of x times psi of x. Just in case this wave function happens to be a complex function, we need to take the complex conjugate times psi in order to get a real quantity. So anytime you have a given number that is complex, if you multiply the two conjugates together, a plus bi, a minus bi, you're going to end up getting a real quantity. So we want a real quantity when we square this, which is why this complex conjugate shows up. If psi happens to actually end up being a real function like cosine of x, then it's not a problem. The square is just cosine squared of x, because the conjugate of something real is the thing in itself. So the conjugate of 5 is 5. So it's not a problem, but we place this conjugate there simply just in case psi is complex. Okay, now, so the square of the amplitude represents the intensity of the wave, so we have this thing. Now our problem is, how the heck are we going to interpret intensity? What does intensity mean when it comes to a particle? Okay,